Dr. Erik Wahlen from Lund University. The title of lecture is this large amplitude solitary waves for the Witham equation. Dr. Wahlen, could you start, please?
Okay, I will start. Thank you very much for the kind invitation to the seminar. And there will be some things which I've seen in Mats' talk already. So I think I have too many slides, but maybe I will go through some of them more quickly because you've already seen it then. Okay, so all of this is joint work with my PhD student Jen Trong and Miles Wheeler from okay, I see this is all information. He's now in Bath in the UK. Okay, so I will talk about, so the Witham equation I'm talking about is without surface tension. And okay, so the motivation for this work can be seen from the full water wave problem, where you probably all know of Stokes' conjecture about the existence of a highest wave with a crest, well, with a corner at the crest with a 120-degree angle, and this was proved about 100 years after the original conjecture by Amick, Frenkel, and Toland, and independently by Plotnikov. So they did it sort of both in the periodic and solitary case. So there were actually two Stokes conjectures, the other about convexity. I will not talk so much about that, but that was done then 20 years later, proved 20 years later by Plotnikov and Toland. So, well, so part of the motivation for this work is to think about what happens for different type of model equations. So a classical model equation is the KdV equation. So if we look at its traveling waves, let's say either solitary, it could be also periodic, but then there is an additional integration constant, so which I set to 0 here. So, well, then you get the simple ODE, and this ODE has only smooth solutions. So you cannot get a similar highest wave with a corner. Right, so this was somehow also in Mats' talk. So the dispersion relation for the KdV equation is just this polynomial relation. And I will get back to that. So connected to the Witham equation in the next slide. So if you look at the full water wave problem, then we know that we have this. Well, if you look at unidirectional waves moving in one direction, and this is the corresponding dispersion relation. And we see that the KdV relation is sort of the Taylor expansion of the one for the water wave problem at the origin. So they behave similarly for long waves, but if you look at shorter waves, so where the wave number is larger, then there is a larger discrepancy. And that is part of the motivation for the Witham equation. This is sort of, I've written it on the same form as Mats, but I call the operator M of D. I would sometimes call that L. So Witham proposed this general equation with the same nonlinearity as the KdV equation, but where we replace the linear dispersive term by a general Fourier multiplier. So with a symbol M, and you can also write this as a convolution with an integral kernel K. And you could allow K to be a distribution rather than a function, which allows you to also include the KdV equation in this general sort of framework. So the dispersion relation would simply be that the wave speed, the linear wave speed, is just this symbol M. And for the KdV equation, this is the symbol, and the corresponding integral kernel will then actually be a distribution. Okay, so this is sort of the general Witten equation, and then he also suggested a specific one to match the water weight problem, where you use the dispersion relation from the water weight problem. And now there's no T here, so I'm looking at the case of pure gravity waves, zero surface tension. Okay, Mats already said a few things about this symbol, but I will repeat give some more information later. I will repeat a bit of what Mats said. But okay, so maybe I could say, at least what I can say right away is now this actually is a function which is integrable and smooth outside the origin. Okay, so Witten's motivation for introducing this equation was sort of to capture two different things. One was wave breaking, as Mats also mentioned, and the other was to capture the highest wave, which is not smooth. So here are some references on wave breaking, and I had a little bit of time to update with some newer ones. So, but I think Mats already mentioned Vera Herr's result on wave breaking. There have been some other recent developments, and there is this nice work also by Klein and Saul with numerical experiments. There's also a nice paper by John Carter on where he compares the Witten equation with experimental results. Okay, so now let's return to sort of the main topic, which is solitary traveling waves. So then we make the standard traveling wave ansatz. So I will use phi whenever we have a sort of wave profile for a traveling wave, and c is the wave speed. So if we plug this into the equation, we get this, which we can integrate, assuming that phi decays to 0 at infinity, then we don't get an integration constant. We get this equation, which I will call W. And so this equation is sort of not really a differential equation anymore, because L, so it's a Fourier multiplier operator. It's a non-local operator, and it's of negative order. So negative order minus 1/2, as Mats mentioned. So Witten conjectured or claimed, you could say, that the Witten equation has the highest traveling wave, which also has a singularity at the crest. But the difference compared to the full water wave problem is that it's not a peak with an angle, it's actually a cusp. So the angle is, the enclosed angle is 0, so to say. It has infinite slope. And he actually also gave sort of some asymptotics of how the solution should behave at the crest. So it's actually this sort of square root behavior. I mean, if you ignore this square root, just had an absolute value of x, then you would get an angle, like in a full water wave problem. Okay, so this was, I mean, he had some formal arguments for this, but it wasn't a rigorous proof. Okay, so I can say some of the heuristics here. Okay, I should, sorry for this. This mu here should actually be a C, so that's a typo. Okay, so some of the heuristics here is that if you rewrite the equation a little bit, so you essentially complete the square, then you see, so then we get the square here on the left-hand side, and on the right-hand side, we have a nice smoothing operator. So here we sort of gain regularity. So whenever we can sort of take the square root of both sides, we can do a bootstrap argument to show that if we start with a solution with some low regularity, it will actually be smooth. But as soon as phi reaches c/2, then this argument breaks down. So that's at least a heuristic argument for why we get the singularity when phi touches C/2. Okay, and so we, together with Mats, we proved this Witten conjecture in the periodic setting a couple of years ago. So we proved more. So for each P, we actually constructed a global bifurcation curve going from a trivial solution to a highest cusp wave. And we were able to say something about the behavior of this solution at the crest. So it behaves like sort of like Witten suggested, with a square root of x behavior. We also conjectured some more precise asymptotics, which you can get from sort of assuming that there is an expansion of this form, you can then compute what this coefficient has to be like. And you can actually do more things here. You can also compute some further terms. So we conjectured this, and we also, like Stokes, we conjecture that the wave is convex between the crests. Okay, and this has actually been proved now. It's still a preprint by this Spanish group, and their proof relies on some computer-assisted estimates. So that's a very rapid development after our paper. Okay. Okay, so that was in the periodic setting, and now let's return to solitary waves. So there are also some results regarding small amplitude solitary waves for the Witten equation. So together with Mats and Mark Rose, we proved using variational methods the existence of small amplitude solutions. This had the advantage that we also got some information about stability. And then there are also results on some very nice results on symmetry and decay of supercritical solitary waves. So supercritical here means with wave speed greater than 1. So that's similar to the water wave problem, where you have sort of the Froude number has to be greater than 1. Okay, and there's also an alternative existence proof using the implicit function theorem for small amplitude solutions. But what I want to focus on is primarily large amplitude solutions. So this is a joint paper with, as I think I already said, with Chen and Miles Wheeler, which was published this year. So we were sort of the main result is that we proved that Witten's conjecture is also true in the setting of solitary waves. And again, we actually construct a whole sort of curve or family of solutions going from the trivial solution up to the highest wave. And this is sort of a picture of what the wave looks like. So it's monotone from, let's say, monotone increasing from, say, minus infinity to 0, where we have the crest. And it's also smooth outside the origin. And actually, it's exponentially decaying. And then at the crest, we have the same sort of behavior as in the periodic case. Okay, so that's what I'm now planning to talk about. My plan is to give you some idea of the proof of this result. And sort of an outline is that I will first talk about some properties of the integral kernel. So this will be a bit of repetition of what Mats said. Then I will actually go through a new construction of small amplitude waves. So even though there are 2 other constructions already, it turned out to be useful to have a third construction, which works well together with the global bifurcation theory. Okay, and then finally, I will say something about global bifurcation. So actually, sort of the analysis of the highest wave with the singularity, that is actually more or less already covered in the paper that Mats and I wrote. So once you have the existence of the highest wave, to get this detailed sort of result about the behavior at the crest, that is actually already done. So we didn't have to do that again. Okay, so first of all, the kernel. So there are some things which were in Mats' talk here, but so again, let me repeat that the kernel is sort of the inverse Fourier transform of the symbol, and that's, I mean, to actually compute this looks a bit difficult. It's not something you compute in your first course in Fourier analysis or complex analysis, but it turns out that you can actually compute it you can get some formula for it using sort of path, sort of complex analysis tools and deforming paths in the complex plane, which leads to this formula. And okay, this doesn't look so explicit either, but it actually, from this, you can see a lot of things already. You can see that, so you have an infinite sum here, but you see that each term is, for example, positive. So that immediately gives us positivity. And you can also prove monotonicity properties. So actually, we have the same sort of behavior that Mats mentioned for the capillary Witten equation in the case where you have very strong surface tension. So that this is completely monotone. And you can also see from this, for example, that it's exponentially. I mean, if you just sort of look at the first contribution in this series, that will be from n equals 1, and you can see from there that you have this sort of exponential decay in x. Okay, so this is one way of proving properties of k. There are also other ways you can do it. And then, as Mats mentioned, you can also pretty easily show that k can be written as a sum of a term which is like 1 over the square root of x, then plus actually an analytic term. Okay, I think this was the exponential decay I mentioned, and then complete monotonicity. Okay, so these things are used heavily in the proof. I will not go into exactly how they are used, but they are important. Okay, and then the other part I mentioned was this new construction of small amplitude solutions. So I mentioned there is already a variational construction, and there's an implicit function theorem argument. So if you look at the water wave problem, for example, then in addition to these two, a very classical construction of sort of solitary and periodic traveling waves is to use the method called spatial dynamics, where you sort of think of your, I mean, you have an elliptic partial differential equation with some boundary conditions. So it's actually a stationary problem, but you think of that as a dynamical system where one of the spatial horizontal directions plays the role of time. So you kind of think about the solution evolving in, let's say, the x direction. And this is then combined, so then you can use methods for infinite dimensional dynamical systems, and in particular you typically use center manifold theory to locally reduce to an ordinary differential equation or a system of ordinary differential equations that you can analyze. Okay, so and this is sort of the philosophy behind our construction as well. So the difference compared to the full water wave problem is that we're not really starting with something where there is that can be written as a dynamical system in an obvious way. So, okay, I mean, we have X, which is, again, is a sort of spatial direction. So we would somehow like to think of that as time. But I mean, we don't have in contrast to KDV, for example, we don't have an OD to start with, and we don't have a PD either. We have sort of a nonlinear pseudo-differential equation. But it turns out that there is a very nice recent theory by Fay and Scheele exactly for this situation, where sort of center manifold theory without a phase space. So we can base our analysis on their approach. So this is what we did. And we had to make some modifications, but essentially we followed their arguments. So what one does is to consider the Witham equation, the stationary Witham equation, in exponentially weighted function spaces. So this, if you know something about center manifold theory, this is very similar to what you do there. I mean, you allow for some mild exponential growth at infinity, and then you also, typically what you do in center manifold theory is that you introduce some form of truncation or cutoff operator of the nonlinearity, so that it becomes bounded, and then you use some form of fixed point argument to construct solutions. So that philosophy is similar here. So what is important in classical center manifold theory is eigenvalues, or the spectrum along the imaginary axis. But if you think about the linearized problem, what you're really after is sort of solutions which are sort of at most algebraically increasing in the time variable, or let's say it could include some exponential growth, but very mild exponential growth. And that corresponds to the exponentially weighted function space that I mentioned here. So similar, then what one has to do is to analyze the linearization in an exponentially weighted function space. And if you do that, it turns out this is a Fredholm operator with index 2. So it is surjective, but it has a kernel, and this kernel is spanned by the function 1 and x. This is pretty easy to see. So you see, we allow some algebraic growth at infinity. And so what one does then is to modify the equation a little bit. So we introduce this sort of cutoff operator that I mentioned to make the nonlinearity bounded. And we can then solve this system. So here I've written 1 plus epsilon. This is really the speed. So we're looking at bifurcation from the trivial solution, but at the critical wave number, which is c equal to 1. Okay, I forgot to mention that here when I talked about the linearization. This is, so the 1 here, 0 stands for linearizing around phi equals 0, and the 1 here is when c is equal to 1. So then we can actually solve this problem where, so this index 2 means that we can add 2 conditions here. So we add sort of initial conditions, the value of phi and the derivative at the origin. So this is like thinking of this equation as an ordinary differential equation, where, I mean, this is typically what we expect for second order ordinary differential equations. So this can be uniquely solved. And then this allows us to construct the center manifold parameterized by these values a and b. And more, so what is it? So we introduce this cutoff operator, and what is important is that if you have a solution which is sufficiently small in some Sobolev norm, and here it should be, well, you need to control free derivatives in the, let's say, L infinity norm. So if the solution is bounded and sufficiently small, then actually this cutoff operator is the identity. So this means that we actually get the solution to the original equation. Okay, so that's nice, but I mean, still this sort of looks a little bit intractable. I mean, it looks difficult to actually analyze the solutions to this problem. So what is even more interesting is that we can actually relate that the solutions will actually solve an ordinary differential equation. And this is because the center manifold is connected to a dynamical system. So this map from sort of the initial conditions to the solution, this defines a dynamical system. So you have a flow map, and once you have a flow map, there will also be a connected ordinary differential equation. So if phi is a sufficiently small bounded solution to the Witten equation with wave speed close to 1, then actually the solution will solve a second order ordinary differential equation. So this is a bit remarkable. And now I say this for the Witten equation, but you can actually show a similar result for the full water wave problem. Okay, so this equation that you see here is now very familiar. If we ignore the right-hand side, this is essentially the stationary KdV equation. So that means that we can then, by perturbation argument, just go from solutions to the KdV equation to solutions of the Witten equation. So this gives us, for small amplitudes, a solution. I mean, sort of the famous perturbation of the famous KdV set-square solution, which then also is a solution to the Witten equation. Okay, so that was the local theory. So now in the remaining minutes, I want to say something about global bifurcation. And here we rely on a sort of abstract framework. So this is by Shen, Walsh, and Wheeler. And so it's not so important with all of these things, but so the main problem with doing global bifurcation theory for solitary waves is that you have to deal with problems with compactness. So if you look at periodic waves, you typically use compact embeddings of, I mean, either you are dealing with sort of in the most classical theory, you're dealing with a compact perturbation of the identity. So, I mean, you need some sort of compactness in the problem. And that's, so, I mean, in many cases, that just comes from compact embeddings, say, between Sobolev spaces or Hölder spaces. But when you're working on the real line, it's not enough that, that you have to look at the regularity. There's also problems with compactness coming from sort of translation invariance. And that things can run off to infinity. So what Shen, Walsh, and Wheeler did was to write down a sort of abstract result, which you can apply in these situations. And this is based on analytic global bifurcation theory, which they have adapted. So the setting is that you have two Banach spaces, X and Y, and then you have some open subset of X cross R. So this is sort of the space in which your functions are living in, and R is stands for the parameter, so the wave speed in our case. And as I said, it's based on analytic bifurcation theory. So the nonlinear operator is assumed to be analytic. Okay, and the hypotheses are that you start. The linearization of the operator at the solution is Fredholm of index 0. So that's one main hypothesis. And the other one is that you have a curve of small amplitude solutions to begin with. So this is what we have now already constructed using the center manifold approach. And then you also need another technical assumption, which is that the linearization at these small amplitude solutions is invertible. So with those hypotheses, you can prove the existence of a global bifurcation curve. And you can characterize what can happen with it in the sort of large amplitude limit. And then there are also some nice, so what's nice about analytic global bifurcation theory is that you actually get a curve of solutions. And in other global bifurcation theorems, you just get a connected set. Okay, so what is a bit special about this result is that is this second alternative here. So this is sort of typical things that can happen, that your solution blows up in the function space, that your parameter blows up, or, well, you can also get blow up by approaching the limit of the set U, the boundary of the set U, which you are working on. But in this case, when we're thinking about solitary waves, there is this loss of compactness alternative, which they include. So even if this quantity remains bounded, it could be that you don't have a convergent subsequence. So this is the thing you would not get in the periodic setting. Okay, I don't know. Yeah, maybe I can go on for a few minutes and to say something about how we implement this. Okay, so I can at least say something about the function spaces we are working on. So it turns out to be convenient to work with free derivatives. This actually is mostly related to the local bifurcation theory, which I mentioned. So in order to be able to rewrite things as an ODE. And we also work with even functions. So this is just because, I mean, otherwise you can also translate the solutions and then you have problems with uniqueness and so on. And then this open set that we work in, the most important thing, well, there are two things included in it. One is that we include that the wave speed is that we're working with supercritical waves. So the wave speed is greater than 1. And that we are also including that we're below the highest wave. And then this is our nonlinear operator, and it's easy to show that this is an analytic operator. Okay, so as I already said, the existence of this local curve of solutions, this follows from the center manifold theorem. And you can also show that this derivative along solutions is Fredholm of index 0. And this might be a bit confusing to you because I previously mentioned that it was, at least when we linearized at 0, that it was Fredholm of index 2. But that was because I was working in a different function space. So that was when I was working in this space of exponentially weighted function space. So if we work with regular Sobolev spaces, then the index is 0. And this is also assuming that C is strictly greater than 1. That's another thing which is important. Okay, maybe I'll skip this technical thing. So maybe I'll just very briefly say what kind of things we use. So what we want to do is sort of to do two things if we go back to this result. Sorry. What we really want to do is to prove the existence of a highest wave. So we want to exclude this loss of compactness alternative. And then we want to show that if this happens, actually we get in the limit a solution which is a highest wave. So where phi at the crest is equal to C over 2. So the kind of ingredients that go into this are some a priori properties of solutions. So then I refer to these two papers. So for example, we use that the solutions are positive, that they're monotone decreasing, that they're smooth as long as we're not at the highest wave, this exponential decay, and that you can also get an a priori bound on the wave speed. So the wave speed cannot go off to infinity. And if you combine these things also, you can also show that, okay, it's not maybe obvious from, well, it is because we're assuming also that phi is bounded by C over 2. So if you combine that with this, this proves that the solution is a priori bounded between 0 and 1. So also the norm, the L-infinity norm of the solution cannot go to infinity. So I mean, what we want, of course, is sort of the we want this Hölder 1/2 norm to go to. And that's exactly where we should see the singularity. And also we want sort of phi to approach C/2 in the limit. Okay, for this to exclude a loss of compactness, maybe I will just say that there is an important integral identity which comes into play there. So in addition to these properties I mentioned before, we use this integral property identity, which you get from sort of just integrating both sides of the equation and noticing that some term integrates to, well, okay, so L of phi integrates to the same as phi. So one can replace the integral of L of phi by the integral of phi. And it may not, if you do, this is the first time you see this identity, may not be so obvious why this is useful. But one thing we use it for is with this to exclude loss of compactness. So what you can see from this is that if we assume control of the L2 norm, and we assume that the wave speed is sort of bounded away from 1, then actually we get control of the L1 norm of phi as well. And if you combine that with some other things, well, if you combine it with control of sort of the L infinity norm of phi and some monotonicity properties, you can actually use that to extract the convergent subsequence. And so we don't have this loss of compactness. Okay, and then the final step is to interpret these blow-up alternatives. So if one analyzes this, one runs into 4 different subcases. And what we show then is that actually that 1 and 2 cannot happen. So one is that the solution actually goes to 0 in the norm. The other is that we reach this sort of critical wave speed 1. So we show that these 2 cannot happen. And the third and the fourth is that the solution explodes in a function space, and that, well, we reach this highest wave with sort of where the value at the crest is C/2. So we show that actually 3 and 4 are equivalent, so that both of them happen. So then in the limit, we get the solution which does exactly what we want. It is the highest wave. And well, okay, so it actually follows by not from our arguments, but by previous result that it's exponentially decreasing. Okay, and as I said, the fact that there is a cusp at the crest that follows already from the results in my paper with Mats. Okay, so that was it for me. So thank you very much for listening.
Thank you very much, Erik. Thank you very much, Dr. Wahlen. A very nice presentation. Okay, so now let's open questions and comments from the audiences. Do you have any questions or comments?
See, there is a question from Ola.
Yes, please.
Hi. Do you hear me, Erik?
Yeah.
Yes, I can hear you. Yeah.
So this is more of a basic question, but when you said that when you changed to this spatial dynamics, spatial dynamics perspective, you said that this mapping that maps the initial conditions to the solution satisfied an ODE. Could you explain that again? I didn't understand that.
Okay, yeah, I'll try to explain it. Yeah, I mean, so this is actually a general property. I mean, whenever you have sort of a flow map for a continuous dynamical system with enough regularity assumptions, then the solution will satisfy an ODE. So that right. You can, yeah. So that was my brief explanation, but so yeah, I don't know if I have a very good intuitive answer other than that, but yeah. So somehow it is because this problem is well posed, and that it defines a dynamical system, then automatically there has to be an ODE. I mean, then of course you have to be able. I mean, the question is then, can you actually compute sort of the ODE? Because I mean, just satisfying an ODE, I mean that if you cannot compute the sort of the right hand side, then it doesn't give you so much. So what we can do is to actually give an expansion of the right hand side as well.
Okay, and it's when you say it satisfies an ODE, you mean so it's not like in is it like a series expansion ODEs, and it's like with infinitely many terms, or is it?
No, so you can express it with this flow map. So I mean, it's more or less, I think it's the sort of the differential of the flow map which shows up. So it's just that you don't know this. So it is a specific function, but I mean you don't. It's something you don't know. It's not so explicit, but you can give a Taylor series expansion of it, which you
Okay.
can.
Okay. I understand. Thank you.
Okay, thank you very much. Any other questions? Yes, please.
Yes, so I have one or two questions in the comment. So actually related to Ola's question. So this second order ODE. So why is it second order? So is that a theory that makes it second order, or is it related to KDV? Because you mentioned KDV, the steady KDV, right?
It is related. Yeah, I mean it's related to this fact more or less, which is also related to the KDV. I think sort of both of them appear when you sort of look at the linearization of the, let's say, water wave problem or the Witten equation at this critical wave speed. So then it's related to sort of the dimension of this of the kernel essentially. So if you look at the capillary with them, so I mean this is something you know of a little bit. So in the capillary gravity with them case with small surface tension, then you could get a higher dimensional kernel, and then you would get, so for example a fourth, you get dimension 4, and then you would get the fourth order ODE.
Yeah, okay, so I didn't recall that from, so I guess Chen had that in her talk. I just didn't recall it. Okay, so that it's not a theory, so it's really the underlying dynamics of the equation, right?
Yeah.
Okay. So
I mean, this theory can work in, I mean, you can essentially have arbitrary dimension.
And then a question concerning uniqueness. So I guess this method, I mean, for small solutions, so the method we're looking at right now, I mean, the local bifurcation, that sort of gives you everything, right? I mean, it's a characterization. I mean, this ODE is equivalent to the full system. But do you know anything along the graph the curve, I mean? Is it with your theory, is it anything you can say? I mean, could there be many different curves?
No, I think there could, let's see. No, I don't think it gives, I don't know. It's basically the answer. I don't think this theory gives anything automatically. So it only requires that the linearization is Fredholm, but I mean, okay, there could be a kernel at some point. Fredholm index 0. I mean, could be a kernel and then secondary bifurcations. But I guess you don't see, how is it for the pure gravity with them equation? You don't see any secondary bifurcations, or how is it?
I mean, like globally, I don't know any equation where one does really have complete control.
No, I mean numerically.
Yeah, no, numerically you don't see, but it's all like for large period, right? But
yeah, right.
So, and then the final just a comment. I mean, you had these two constants, C1 and C2 at the very end. So in, I'm just mentioning it now, so since Ola just defended, but in his final paper, in his thesis, these two are determined to be the same constant. It's just not on archive yet because I need to add a part as well, but they are determined to be the same, which could help, for example, uniqueness of the highest wave, but not along the curve. Yeah.
Very nice.
And they are the same constant as we hope.
Yeah, no, it's not that I doubted that it would be the same constant. It's just I didn't want to write something which I couldn't back up.
Of course.
Now I can refer to Ola.
Yeah. Very nice talk. Thanks.
Thank you.
Okay, thank you very much. Any other questions or comments? I have a very primitive question. This highest wave is a limit point of this global bifurcation curve. Is it correct? Yeah. And my interest is in the outskirt. In the outskirt, solitary wave solutions decays exponentially. And my interest is the decay rate of this exponential decay. And I think this decay rate decreases with decrease of wave amplitude. Is it correct? It's a decay rate is all the same value, but I think it depends on amplitude, right? This decay rate.
Yeah, I think Mats knows this probably better than I do.
Actually, it's my interest is about it's the singularity of small amplitude limit of solutions.
Yeah. Okay. Yeah. Then the decay rate sort of goes to.
Is it related to the singularity?
So, okay, I'm not sure if I understood your question. So,
what causes singularity of small amplitude limit of solutions?
Yeah. So that when C approaches 1, you get run into problems.
Okay.
I think this sort of I wrote C equals 1 plus epsilon, and the decay rate involves epsilon.
Okay. Okay. I think you I got it. Okay. Okay, thank you very much. Any other questions or comments?
Can I have can I ask one question?
Yes, please.
Thank you for nice talk. And you proved the existence of the largest solitary wave, right? And is this unstable or stable?
That we don't know.
Okay, but you mentioned that there are solitary waves of other.
Okay, so I think Mats has something to say. I mean, I don't think there is a rigorous proof of anything, but maybe there is numerics or.
Yeah, so numerics says, but that's for any fixed period. It could be large. Says that they are becoming unstable when you approach the highest. So there is a maximum L2 norm which happens before you reach the highest, and there numerically they start being, but there's no proof.
Let me confirm again. So you mean that there's a critical amplitude at which the exchange of stability occurs?
Numerically, yes.
Okay, thank you.
Okay, thank you, Dr. Kataoka. Okay, any other questions? Okay, thank you very much, Erik. Very nice presentation.
Thank you.
And again,